Time to get started. My name is Tom Koselman, and I am the interim dean of the School of Natural Sciences. And I'm here to announce our speaker for our first natural science seminar of the year at Spring Arbor University. Our speaker is Dr. Hauger, who earned 2 degrees at Illinois State University, a bachelor's in mathematics and then a master's degree in mathematics. And she went on to Michigan State University. Actually came here in the fall of 1971. That's when she started teaching. Do the math. That's 49 years here. That's really cool. While she was working here, you got a master's degree at Michigan State in probability and statistics, and then a PhD in mathematics education. And she's going to tell us a little bit about the math that went into the Moon Space Program. It might have been a little bit involved, I think.
Whatever.
Dr. Hauger.
Some of you may realize that last January was the 50-year anniversary of the United States putting men on the moon. There were lots of programs on TV for that. PBS had a 3-part series on that, as did the Smithsonian Institute, and wherever there was a space program on TV, I was watching it because I was enthralled with this whole process. So we're going to talk a little bit. This is timely. We're going to talk about a little bit about this. Now, before NASA came into being in the late 50s, early 60s, there was a serious balloon effort to put people into space. And there's a PBS special on American Experience about that, which I also found fascinating. One of the people in David Simmons in 1957 managed to get up to over 100,000 feet to what's called the edge of space. Now that's no big deal these days because science can't put a balloon up to 100,000 feet one year. We got to see that edge where it goes from blue to purple to black. Pretty awesome. And here's some other statistics. 62 miles up is considered the Earth's boundary ends and suborbital space begins. Low Earth orbit begins about 1,200 miles, and then at that low Earth orbit, it takes anywhere from 84 to 127 minutes to orbit the Earth. There are all sorts of types of orbits we could talk about, but that's not what we're talking about today. Okay, so the Soviet Union, they kind of beat us at this game initially. In 1957, they put up Sputnik, an unmanned satellite. It went into low Earth orbit for about 3 weeks until its batteries ran out, and then it just sort of meandered around in low Earth orbit until it fell back into the Earth's atmosphere, and that was kind of a shocker for us. Not many people in this room would remember looking out their windows and seeing this light going. I'm getting goosebumps just remembering my dad and I standing at the window watching this thing go across. He goes, "Do you know what that is?" And I go, "Sputnik." And I'm going to be up there, Dad. It's looking like you're a nut kid. Okay. And then in 59, the Soviets launched Luna 1. It became the first spacecraft to reach the moon's vicinity, and it provided communication up to 500,000 kilometers away. That's beyond the moon. It gave lots of information to us. And then the Soviets were the first group to put a person into orbit around the Earth. Yuri Gagarin in '61. They called them cosmonauts. We call them astronauts, but don't big details. Okay, so he did in fact was launched into Earth orbit and completed 1 orbit of the Earth and was safely brought back to Earth. In the meantime, what was the United States doing? Well, if you've seen, it's not really funny, but I have to laugh. If you've seen the videos of our early efforts, you see rockets explode on the launch pad. You see rockets go up and then crash back down. You see rockets go up and then explode. And then you see rockets go up and then they go off where they're not supposed to go. It was a comedy of errors if it weren't so tragic. But finally we got our act together enough that in 1958 we launched Explorer 1, our first unmade satellite. So that went into Earth orbit. And then shortly after that, April '59, 7 astronauts were selected for the Mercury program. Some of these names you might recognize: Alan Shepard, Bernard Grissom, John Glenn, Scott Carpenter, Wally Schirra, Gordon Cooper, and Donald B. Slayton. So then they began, not me, they began working on Saturn rockets. Yeah. Okay, so we were behind. Why would we care that we were behind? Today, we have some more exciting things going in terms of international cooperation, but in this post-World War II era, this was called the Cold War era, and there was lots of mistrust and back and forth between the Soviets and the United States. So this was a serious time in terms of who can be first to space, because the first country that gets to space is going to be the first country who can create and launch weapons from space, and that would be a pretty serious thing. So we began to give serious contention to, hey, let's get our act together here. So in 1961, President Kennedy issued a challenge to Congress. He gave the same challenge at Rice University later in that year or early the next year, that we wanted by the end of the 60s to put a man on the moon. Now you may say, oh, big deal, we've done that several times, what's the big deal? Well, we'll see in a minute that the big deal is we didn't have any of the problems solved that would help us do that. I'll have a bunch of questions posed here in a minute, and we didn't know answers to any of these questions. It seems sort of simple-minded now, given that we have fantastic probes, telescopes, shuttles, rovers, we have the International Space Station. These are not all international events, but they are often efforted by lots of different countries. How many of you saw the PBS special about the astronaut, can't remember his name, he's a twin, and he spent a year in space. Scott, and they were talking about every 3 months they're supposed to send up a capsule that will resupply the International Space Station. The first one from the Russians failed. The second one from the United States failed. Now we're going into 9 months. The Japanese finally got one up to the International Space Station to resupply. So you can see this is an international effort. But and some of you may have seen the Horizon probe recently going past Pluto. Again, goosebumps here. Pretty exciting stuff. Yeah, lots of things going on. But in 1961, these were not part of our world. We did not have these successes, and international cooperation was way off. Okay, so when Sputnik went up in '57, the United States realized its predicament. I was in middle school then, 6th grade, and quite fascinated by it all. I could not get enough. And over the next few years, money became available to upgrade math and science instruction in high schools and colleges. We got new textbooks in science. I couldn't believe it. When I went to school in the 8th grade year, and there was this nice-looking physics book, I was excited. I was the beneficiary of this money that became available. So we finally got our act together. In 1961, Alan Shepard went up and down. He did not go into Earth orbit. They simply shot him up, so we did that without problems, and he came back down 15 minutes later. He reached a peak altitude of 116 miles and a top speed of 5,000 miles per hour. And just to make sure we had that right, we sent up Virgil Grisham a little bit later. He also went up, came back down, 15 minutes and 27 seconds. He reached an altitude of 118 miles, so he had the record at that point. We had not yet put a person into Earth orbit. So, because we had lots of questions we did not have answers to. Here's a bunch of them. How can we get a manned space capsule into Earth orbit? A larger question is, once we get it there, how can we get it back? How long can an astronaut survive in Earth orbit, and what does it do to the astronaut's body? How do we dock 2 space capsules while they are in Earth's orbit? We had to do that because if we're going to go to the moon, we're going to have to send down a lander, and it's going to have to come back and dock with the mothership, as it were. So we had to solve that problem. And there's some interesting video about how that didn't go so well the first time. Okay. What problems have to be solved to do a spacewalk? The first person who did a spacewalk, I forget who it was on the U.S. side, didn't want to come back in. They had to issue a military order to get him back into the capsule. So it must have been a lot of fun. I wanted to do that. How can we get a space capsule out of Earth's atmosphere and on the way to the moon? We're going to solve the differential equation that will show you how to do that. I know you're excited. How can we get a space capsule into orbit around the moon? How do we send a lunar module to the surface of the moon with a soft landing? I have a handout in case some of you want to take that differential equation with you at the end. How do we get the lunar module back to the module that is orbiting the moon so they can dock? If you're sitting on the moon, you want to make sure you can get back to that orbiting capsule, right? I will. How do we get out of the moon's orbit and headed back to Earth? How do we get out of deep space and back to Earth? Okay, first two questions. How do we get a manned space capsule into Earth orbit? Second question, how can we get that capsule safely back to Earth? Accounting for atmospheric drag, a rocket must achieve a speed of about 21 miles per hour to get up into Earth's orbit. That's what they tell me. I'm not going to... 21,000.
21,000.
Yeah. Did I say 21?
Yeah.
Well, how embarrassing is that? Okay. Yeah. My Saturn will go faster than 21 miles. And once it reaches orbit, it can stay in orbit with the speed of, now this sounds like precise, but this is what Katherine Johnson said it is, so it must be right. So, and you'll see her say that in a few minutes. 17,544 miles per hour. The International Space Station is in low Earth orbit and travels at 28,000 miles per hour. And if the speed is less than that, it will fall back to Earth. We don't want that to happen. And you may question, why this number?
Yeah.
Why that number? Hold on. Okay, we'll get to that. John Glenn was the first American to orbit the Earth in 1962. His flight was almost 5 hours long. It was supposed to be longer than that, but a problem developed in the third orbit, and they needed to bring him down. He was safely brought back to Earth. How do we get him back to Earth? Well, here's two key people. Well, there's John Glenn. He's a little blurry. There's John Glenn, the astronaut. Here's Katherine Johnson. She was one of the colored computers. And if you have seen Hidden Figures or read the book Hidden Figures, you know that there was a, thank you, Mr. Dr. Baldwin. You know there were a lot of women who were considered computers, and there was a group of colored computers, we're talking about African Americans, who did a lot of the work. And she was responsible from 1958 to 1986 when she retired for determining the trajectories of almost all of the space flights. If you can get some of her papers on the internet if you want them for good reading during a football game or whatever. Okay. She was responsible for answering most of those questions that were on the earlier slides. Now, John Glenn was naturally concerned about the answer to the second question.
Amen.
Can you get me back to Earth, please? And he wanted Katherine Johnson to double check those calculations to make sure she got them right. Here is, I want to show a couple of video clips from the film Hidden Figures. So,
Morning.
let's just speak about this. Hope you can hear this.
This is Catherine Goebel with our Trajectory and Launch Window Division. Her work is pertinent to today's proceedings. I'll get her a chair. We have a confirmed launch window. Get her a chair, please. We have a confirmed launch window for Friendship 7. Let's discuss a landing zone.
The Navy needs a singular landing zone.
20 miles square is where we can service for retrieval. Outside of that, we risk the capsule's recovery.
We'd like 3 possible recovery areas.
We can't cover half the damn ocean.
With all due respect, our capsule is being altered daily. We're orbiting the Earth at what speed now?
$17,544 miles per hour at the time the rocket delivers the capsule into low space orbit.
Well, that's one hell of a speed to you. Okay, so we have the vehicle speed, the launch window, and for argument's sake, the landing zone is the Bahamas. Should be enough to figure the go, no go?
Yeah, in theory, sir.
We need to be past theory at this
We'll
point.
be able to calculate a go, no go with that information.
When exactly is that gonna happen? Catherine?
Have a go at it?
The goal point for re-entry is 2,990 miles from where we want Colonel Glenn to land. If we assume that's the Bahamas, it's 17,544 miles per hour. Upon re-entry, 307 feet at a descent angle of 46.56 degrees. Distance velocity squared, sine gravity. Sine 32 feet. And distance is 20,530,372 feet, or 2,990 miles, or 46.33 degrees. Okay, so that puts your landing zone at 5.0667 degrees north, 77.3333 degrees west, which is here. Right here. Give or take 20 square miles.
I like your numbers.
Thank you.
That, of course, is assuming the capsule hits the re-entry point exactly. How do we ensure that?
Well, that's the math we don't have yet, gentlemen.
Don't have that math yet. Oh no, what's gonna happen now?
I want to know.
Me too.
Okay,
Seconds.
Planck Einstein.
The problem is when the capsule moves from an elliptical orbit to a parabolic orbit. There's no mathematical formula for that. Because we can calculate launch and landing, but without this conversion, the capsule stays in orbit. We can't bring it back home.
Maybe we've been thinking about this all wrong.
How's that?
Maybe it's not new math at all.
It could be old math. Something that looks at the problem numerically and not theoretically. Math is always dependable.
For you, it is.
Euler's method,
Euler's method.
yes.
But that's ancient.
But it works. It works numerically.
That's it.
Let's type it up.
Of course, she has. Okay.
Okay.
We'll just skip it. Okay. All right. So, yeah, how can we get an orbiting capsule back to Earth? The Earth orbit velocity is given by this formula. We have g, an empirical constant. Please don't ask me where that came from. M is the mass of the Earth. R is the distance from the center of the Earth, not from the surface of the Earth, but from the center of the Earth. So the larger values of R mean smaller values of V. See, you have this R in the denominator. So when you calculate this, if this gets larger, this gets smaller, which is a way of saying the farther away from the Earth you are, the slower you move. So that helps explain those two different formulas we had before for the speed. John Glenn was in a higher Earth orbit. He was moving at a slower rate. And the International Space Station is in a lower Earth orbit. It's moving at a faster speed. So how do you get out of Earth's orbit and back to Earth? I saw a picture that, well, this isn't very good, but the picture, you have an elliptical orbit around the Earth, and at some point, you have to say, I'm going to leave this and assume a parabolic, parabolic fall that will take me down to the comets. So what you have to do is you have to thrust against the velocity vector. You're going along, and I think the capsule has to turn around and issue a thrust to slow it down. And slowing it down makes it fall into lower Earth orbit. So that capsule is now closer to the Earth, therefore it's going faster. And then at the point determined by Katherine Johnson, Glenn manually, I didn't realize that astronauts actually had to fly these things, but they actually had to do things. He had to manually maneuver the capsule out of the elliptical path and assume the parabolic path that brought him safely back to Earth. Now, you might want to know an answer to the next question. Fine, we did that. We can get people in and out of the orbit of the Earth, but how do we get them to the moon? So, in the interest of time, I'm going to talk fast. Newton's law of gravitation, one of his laws of gravitation says that acceleration is equal to this. K is a constant that has to be determined from certain initial values. Little r here is the distance from the center of the Earth. But we have, and when r is, when you have the value of the radius of the Earth, you can plug that into the formula. And when you're sitting on the surface of the Earth, the acceleration is the acceleration due to gravity. So now you have this acceleration is that, but it's also that. So you can equate these two, and you can solve for the constant of proportionality. So now our equation looks like this is equal to that. So let's go to the next slide. Now, it's also the case, good calculus students, this is the place where you wake up. Okay? Good calculus students, you know that the acceleration is the rate of change of the velocity, the derivative of velocity with respect to time. And the chain rule says I can interpose almost any variable I want in here, the rate of change with respect to the distance from the center of the Earth times the rate of change of the distance from the center of the Earth with respect to time. Why would I want to do that? Well, because this is another name for the velocity. Velocity is the rate of change of distance with respect to time. So now we have acceleration is equal to the velocity times the rate of change of the velocity with respect to r, and acceleration is also this. So now we'll equate these two right here. So we got those right there. Looks like I did something else with that. That's kind of cool, I think. Okay. Multiply both sides by dr. Good differential equation students do that, you don't care. Okay, so we've got this equation right here. And now we're going to integrate it from both sides. Now, just put an integral sign right in front of there and right in front of there, and you're home free. The antiderivative of v is 1/2 v squared. The antiderivative of a constant times 1/r squared is that constant times -1/r, and then we have a constant of integration. Calculus students, okay, Sabrina's shaking her head. Yes, thank you, Sabrina. Okay, multiplying both sides by 2 gives us this nice formula down here. Okay, so there's that formula again. Now, let's plug in again some known values. When little r is equal to cap r, that means we're sitting on the surface of the Earth, then the velocity will be that initial velocity that we're hunting for. And we plug those values into this equation up here, get this equation here. We're going to cancel that out with one of these to get, I guess I didn't do that very well here. Okay, cancel that out with one of these, and then solve for 2c. We get that. Okay, so it's the constant of integration. Right up there.
Not the speed of light.
Not the speed of light. Thank you. No. Okay, so yeah, so our equation now becomes v plus this plus 2c. Now, this last thing right here has to be positive. Why? Well, the argument is that the further away from the surface of the Earth you move, the larger r is, and the smaller this term becomes. This term's positive, but if it's becoming smaller and this term is negative, then at some point this is going to beat out this, and v squared is end up going to be 0. And we don't want that. That gets you nowhere if the velocity is 0. So that number has to be positive. Doing a little bit of algebra here. We're trying to solve for v0, and we get this. You may not know where these come from, but I'll tell you in a minute. This is, I believe, the radius of the Earth, and this is the gravitation due to constant and some other thing besides feet per second per second. We'll get to that in a minute. Okay, so you do this calculation, you get all this, you get this, and these two numbers, again, goosebumps coming. When I saw the 3rd episode of the PBS series and they said, well, they had to assume a speed of 7 miles per second or 25 miles per hour, I launched out of my seat and danced around the living room because I knew they were right. Yeah, g is the acceleration due to gravity, and you've converted into miles per second per second. Radius of the Earth is in meters, you convert that to miles, so there's where those numbers came from. So the escape velocity to get out of the Earth's atmosphere and on to somewhere else, 25 miles per hour. You need a thrust. Have you seen the pictures of those huge thrusters at the bottom of that? Yeah, it's pretty cool. Okay, now, how many know how far it is from the Earth to the Moon?
250,000 miles.
250,000 miles.
Plus or minus.
Plus or minus a few feet. Okay, so if you're leaving the Earth at 25,000 miles per hour, how long should it take you to get to the Moon? 10 hours. It should take you 10 hours. Why in the world did it take them 3.5 days?
They use the brakes.
They stopped at a Coney Island on the way.
Ran out of gas.
Ran out of gas. Okay, well, just because you're out of the Earth's atmosphere does not necessarily mean that the Earth doesn't exert a force on you. The Earth's gravity is pretty powerful, and it's going to exert a force on you to slow you down until you get to a point called the Lagrange point. Lagrange is a famous mathematician, probably a famous scientist too, I don't know, but a famous mathematician, so I was happy to learn that at the Lagrange point, the Earth's gravity no longer is such a factor. The Moon's gravity is now a factor, and the Moon's gravity is going to start pulling that capsule, with the help of the astronauts doing some steering, into lunar orbit. Okay, then we've got, did I skip a slide here? Okay, so they get into lunar orbit. Now, they go around a few times. They want to release the lunar lander so that it floats to the surface of the Earth. It'll contain Neil Armstrong and Buzz Aldrin. There's a handout available. I forgot to bring it, but I'll get it at the end. So if you want to look at how you can guarantee a soft landing on the Moon. An important question, because on the same day or the same week that these two guys landed on the Moon, the Russians slammed a lunar lander on the dark side of the Moon into the surface of the Moon at 300 miles an hour. That was less helpful. I don't know if they had any cosmonauts on board. I don't really want to know, but that was scary. Okay. So they spent some time on the surface of the Moon. There's lots of video about that. They didn't spend much time outside the lunar module, 3.5, maybe 4 hours. But it took them 24 hours to get off of the moon because the lever that started the engine for the lunar module to float back was broken off. And so Houston said, why don't you guys take some rest and we'll get back with you. Now, this is kind of important. These guys are sitting on the surface of the moon, and if they can't get this engine to fire, guess where they're spending the rest of their lives? So, Houston solved the problem. The engine started the next day. They go back up. They dock with the capsule that is, with Michael Collins on board, that is circling the moon. Michael Collins is the only human being, well, this is an over-exaggeration, but let me say it. Michael Collins is the only human being who did not see any of the activity that was going on the surface of the moon. He does not have any,
I also didn't, I was
okay.
in Canada, didn't see.
Yeah, okay. So they show lots of pictures of people around the world glued to the TV watching this. I was glued to the TV watching it. And yeah, so they're telling Michael Collins, they're on the moon. He goes, okay, great. I can't see a thing, but okay, that's cool. They come back up. They successfully dock. They continue to orbit the moon. And then when they're ready to come home, at some point on the dark side of the moon, back side of the moon, they issue, they start a thruster engine that increases the speed of the capsule so it can rise out of lunar orbit and assume a path toward the Earth. They reach the Lagrange point, and the capsule comes under the pull of Earth's gravity, and then they're speeding home, I suppose. And then they get into Earth orbit, and once they get there, they know how to get back to the Earth because of the John Glenn, Katherine Johnson problem. Oh, that's all. We're done. Forget that. Okay. Questions or comments? Maybe you know some facts. Questions or comments? Maybe you know some facts about this whole thing that I don't know. Yes.
Okay, so you calculated the escape velocity of the Earth when it goes off the back. Did you by chance calculate or do you know the escape velocity to get ourselves off of the moon?
I haven't looked at that one. I spent my weekend talking about how can I get it down from the moon's orbit to a soft landing. But, yeah, that's another cool differential equation.
Where is the Lagrange point? How far from the moon is it?
It's closer to the moon than it is to the Earth.
Oh, yeah.
I don't know if it's labeled here or not. I can't see. I'm tempted to say there, but I don't think that's right. Yeah, I think it's over here somewhere. This is much larger. This is the moon. It's not that large compared to the Earth. Yes.
We solved these questions for the Mars mission.
Oh, I'm sure we haven't. One of the big questions about the Mars mission, well, of course, having enough supplies, having enough fuel, and all that stuff. But these people are going to have to. One of the reasons they had Kelly at the International Space Station for a year was to say, how long can people survive in space like this without detrimentation? I don't know what the right word is. Without harming their health. Yes. Do you know answer that question?
It's running down. Where do you bring 25,000 miles per hour down?
Okay, I'll get back to your question. Did that help with that? They don't have all those problems solved. They're working. And there's some crazy people who really want to go to Mars. I'm not the one. No, I don't want to. Yes?
So how much did it slow them down?
That's a good question. How much did once they were going 25,000 miles an hour, how much did it slow them down as they went further to the Lagrange point? Well, I don't know, but it took them 3.5 days to get to the moon, so there's some slowing. One of the slides did say how much, or not, one of the articles that I reviewed did say something about that, but I don't remember. Yes.
So in order to dock with the land, they had to execute these, frankly, pretty complicated exercises in space where there's no friction.
That's right.
Oh.
Yeah.
So when you take undergraduate physics, you always do the problems, and then there's more
Assume no
friction
friction.
coefficient in there, and you take, all class like statics or dynamics, and there's coefficients of friction that depend on composition and then how much the area of it is sitting on it. A lot of this was done in water. When they were rehearsing these types of maneuvers. How well, because as we know, water does have some friction, but how well did this mimic mathematically? How well did a water simulation model actually went on stage?
I don't know the answer to that question, but it reminds me of the question I do want to answer. So this is a trick you do on your dissertation when they ask you a question you don't want to. Gus Grisham, I believe it was, it was either his undergraduate research paper at MIT or his master's paper. He had flown a fighter plane in Korea, I believe it was, and he was very successful. Okay, there's fighter planes. Here's an American. Here's a Russian plane or whatever, Korean, whatever, and you want to fire your missile so it hits that. He solved that problem mathematically. And so they put him on this project. Okay, you've done these kinds of things where people aren't even in the same orbit, and so you solved that problem. And the first time they did it, the video is amazing. They docked successfully, and then the mother capsule began to oscillate wildly. So he had to unhook it before he could bring it down. But yeah, I don't know how to answer your question.
When they said Euler's process, I mean, Euler did tons of math.
He did.
How in the world did they do you know what Euler was working on when he came up with the thing that they applied?
Oh, you want me to derive Euler's method, huh?
Well, I want you. What did Euler? Was it just a theoretical problem in math that Euler?
Well,
they
did.
solve something?
Taking a derivative of a known function is not too hard. Okay, messy, but okay. But once you have a differential equation, then it's not necessarily easy to solve that, not using analytical methods. There are a few techniques, but most differential equations are not easily solved. So you need numerical methods. So he said, if I have a starting point and I know how this function changes over the next little bit, then I can predict where I'm at in that little bit. And so he just thought to his mind, what do I have to add or subtract to this beginning point to get me to the next point? The formula is really pretty simple. You want me to write it down?
Sure.
All right. Let's see. To get to the next point, I have to start at the previous point, and now do I add or subtract? This is what I don't remember. Plus or minus, there we go. That's okay. Wow, maybe I don't know it. Okay. Wow. I'm going to put this up here, even though I don't think this is quite right. Yeah, to get to the next point, you have to start at the previous point, and then you have to add or subtract some ratio of the derivative to the function. So this would be, this might actually be the previous, wow, see, I don't remember. Something like that. Come to my office.
What if Catherine had done that in front of the court?
Oh, that would have been embarrassing, especially in the movie. I loved what she did to the Jim Parsons character.
Yes.
Sheldon Cooper got his comeuppance. Other questions or comments? Any of you?
Could they have used wrong cutter method, and if so, why didn't they?
If they had had it then, they probably
They
used
didn't have it then.
Well, the Runge-Kutta method is very effective if you have Excel, for example, or if you have some numerical software package that will just generate. You put on the nasty formulas, it'll generate. Well, doing it by hand would be not fun. Or the Runge-Kutta method over 5, or the Runge-Kutta-Fehlberg method. Those are all complicated, ugly methods. Even with Excel, students screw it up all the time. So yeah, I don't think they may have. It wasn't until later that the colored computers went to the IBM people and basically told them to get out of the way. We're in charge of this now. So I don't think they had that option quite yet. Yes. What is that thing? Euler's method, well, I was trying to write the formula up here, but I screwed it up so bad. It's a, Runge-Kutta method, oh, I'm definitely not gonna write that formula. It's a way of saying, okay, to get from this point, this known point, to the next one, I'm going to not just do the ratio of the previous point to its derivative, but I'm going to do some intermediate points too. I'm going to compute some intermediate derivatives, and it's cool. I'll show you if you want. I have a spreadsheet. Yes, sir.
When you're in the actual Lagrange point, are you being pulled one way or another, or are you just sitting there?
Well, I think they're just sitting there, but I haven't been there myself personally. Yeah, I think they're, I don't know, that's a good question. You have those smartphones?
Yes,
There you go.
If you're being
They're not going like this, I don't
being
think.
pulled both ways, you're sitting there.
Yeah.
The answer's yes.
So your velocity zero, I don't know. Yeah. That's, well, I've seen some people I can't identify what they are, so, okay. Other questions or comments? It's great. Thought-provoking. I just can't get enough of this stuff. I'm teaching differential equations next semester in case any of you care. Yeah, do it. Great stuff. And this stuff is on page 99. It's early in the, it's in chapter 2.
Page 99 is chapter 2.
Chapter 1 basically says, well, here's all the 5 or 6 or 7 analytic techniques we know. And then the rest of the course is numerical. Yes?
This is kind of unrelated, but do you know why, like, the moon is always facing the Earth? Like,
No.
Yes.
Oh, he knows.
Well, because its rotation is exactly the same as the rotation.
Oh.
It rotates as it goes around, so it always stays the same. Because if it didn't rotate, you'd see different sides of it, with my hand. But if you turn your hand, it's locked.
So
It's gravitationally locked.
Gravitationally locked. I love that.
If there are any more questions, you can come on down front and ask Professor Hogger, and thank you for your attendance.